Welcome eNet 130 at Bellingham Technical College. This is our quarter study of semiconductors in our electronics technology course curriculum. And the topic of this lecture is clippers and clampers, which are two very specific types of diode voltage regulators. And these have the function of limiting either the amplitude or the position of the maximum peak or minimum peak value of a waveform respectively. Clippers govern amplitude and clampers govern peak position, so shift a curve up and down. So this is section 3.3 in our James Fiore textbook, and we're going to, as usual, focus on the figures with the highlighted text being for your review. Okay. And for this we're going to focus on, I'm going to try to zoom up and then center. This is what's known as a biased positive clipper. So we've got a time varying voltage source, so we'll just assume it's sinusoidal because most of the ones we work with are. We have a current limiting resistor, and then in parallel we have a diode and some type of fixed DC voltage source, and both the sinusoidal and the DC are grounded. And I've got a label here on node A, which happens to be the same potential as V out, but it's easier for me to think about nodes as having labels because nodes are really where the action takes place in a circuit. And the node voltage here might not have been V out. We might have had some other circuit that it's feeding. But the voltage at node A is super important because it determines, at least partially, whether or not this diode is going to conduct. More specifically, if the voltage at node A is equal to whatever the voltage is here right above the V clip source, only if it differs by 0.7 from the V clip voltage, the diode will turn on. Otherwise it won't, even though it's forward biased for current flow going to ground. So that's what we're going to look at, and that's going to have a big part in the function of the circuit is when the voltage at node A is or is not sufficient to allow current to flow through that diode. So we're going to walk our way around the waveform of the input, and we're going to use these numbered steps of our action plan here. So we're going to start when our sinusoidal waveform is at 0 time and it's 0, and we're going to trace it through the positive half cycle. So during the positive half cycle, the diode will act like an open until the voltage at the node at A is greater than 0.7 volts plus whatever it is right here between the diode and this DC source. So what is the voltage at this point between the diode and the DC source? Well, the other end of the DC source is hooked to ground. So the voltage at this point between the diode and the source is literally the source voltage. So the diode will open when the voltage at node A is V clip, meaning V clipper, offset, plus whatever the forward bias voltage of the diode is, and we're going to assume that it's 0.7 in most cases. So when VA is V clip plus V forward, probably 0.7, we can get current flowing to ground through this path. Until then, all the current would have to flow over the resistor and into the output circuit if it was a low enough impedance path. So the effect of that is that our output voltage is going to track the input until VA gets big enough to allow current to flow. Once that happens, once Vin is greater than V forward plus V clip, the current's going to flow with very little resistance through the diode. Remember, diode is a one-way valve, so we're gonna be on that steep part of the current voltage curve for the diode. And as it turns out, DC sources, especially batteries, have very, very low resistance to current flow through them, especially a time varying signal. So a battery is going to act like a short to ground from the standpoint of any kind of AC signal. So basically we create a short to ground once our V input is greater than this V forward plus V clip. Well, if it's shorting to ground, we're not really going to get much more of a voltage rise than that V forward plus V clip because there's nothing else to drop voltage over. So at that point we're going to have clipped the voltage from the standpoint of the output, and it'll stay there until we drop into the negative half cycle, in which case we would be flowing current back the other way. You can think of it as flowing up through ground, and it's not going to flow anywhere because the diode is in reverse bias. So in that case, this whole part of the circuit kind of just gets taken out of the game, and our output and node voltage will just track straight with our input and resistance. So VA becomes V resistor and is tracks with the input in that case. So important things to remember. When does the diode open? It opens when VA is greater than V clip plus the forward bias. What does that mean from the standpoint of the output? It means that we will have a circuit in which we have effectively moved ground up to that point from the standpoint of dropping any more voltage. And so we've limited the output voltage to V forward plus V clip, and then when can current not flow through the diode? When it's trying to go the other way, and then we basically take this out of the circuit. So those are the things to remember about a clipper. What does it take to open the diode, and over what portion of the input waveform does this whole branch effectively go away, because the diode is open and taking it out of the game. We can do the same thing with an opposite oriented diode and reversing the battery terminal here. So in this case we go from ground to some negative voltage between the diode and the DC source, and now at this point, to get current on the negative cycle of our input to flow to the output, VA has to be less than the combo of V clip and the forward bias voltage of the diode. So what that means is on our negative half cycle we're going to be limited by that combination at our output, and the forward half cycle current can't flow through the diode, so this whole portion of the circuit goes away. So this is called a bias negative clipper, and it's going to affect the negative half cycle. And I've put down the steps to go through to walk you around the waveform for that. So an easy way to take a look at that and get your arms around it is to use our TINA simulator. And so we've put a couple of clippers in this circuit. We have a sinusoidal waveform, which is 12 volts amplitude, so that's 12 volts peak, and it's got reasonably high frequency, which really doesn't matter from the standpoint of this circuit. We've got our current limiting resistor, which can really be any value in this case, but it's pretty high because we don't want to damage our diodes or have excessive AC current flowing through our sources. So we have our forward clipper. So basically current can flow through this diode on the forward cycle if and only if it exceeds 6 plus whatever the forward bias voltage is, and these are silicon, so it's going to be around 0.7. And here's our negative peak clipper. So the reverse cycle can only flow through this once it exceeds 8 volts plus whatever the forward bias is. Again, so we'd expect 8.7 and 6.7 to be our maxima for our negative and positive peaks respectively. So we can run a transient analysis over a couple of periods and see how correct we were. So in this case, our red trace is our output, and the green trace was our sinusoidal input. So again, we had our 12 volts amplitude there, and so we're looking at 1 and a bit periods. So let's use our curve tracer here and and see if we were correct. So we had assumed that we should be clipping at about 5.3, give or take. See if we have that correct on our forward. We have 6. So we have a potential of 6 here. So we'll have to supply a voltage. Ooh, excuse me, math in my head. My voltage at this node is going to have to be the forward bias, which is about 7 plus 6, so 6.7, which my test told me. So my clip plus the forward bias voltage, so that's 6 plus, not 6 minus. Very good. This is a good reason to run tests. So let's make sure our head math was correct over here. In this case, this point is going to have to be less than -8, effectively, minus the forward bias. So we would expect -8.7. So we're hoping to see a -8.7 here or thereabouts. And this time we were correct. So let's take a quick look and see what would happen if we change these offsets. So what would happen if we, say, reversed or reduced this quite a bit? Let's reduce that to 2, and let's increase this to, say, let's increase this to 11. So we can do a little bit of a head math here, see if I can redeem myself on my video lecture. So at this point I would predict my forward cycle to be clipped at V forward plus 2. So I would expect that about 2.7 would be my new plateau. So I would assume it would be clipped much lower. So we can just get current flowing at a much lower onset and therefore not reflect the voltage to the output. And on my reverse cycle, I'm going to need to reduce the voltage of this node to below the forward bias voltage in the negative direction and 11. So I would expect to see almost the entire negative going waveform there. I would expect to see 11 and a bit, and we're imposing 12. So we can run our transient analysis and check ourselves. Aha! It's looking good on the negative end. And here we go, 2.55. So that's 2 volts and something just shy of what we would expect forward bias voltage. These diodes seem to have a forward bias voltage of about 1/2 to 6, or excuse me, 1/2 to 0.6. And we've known from reading some diode spec sheets that forward bias voltage can vary. We typically use 0.7 as a baseline. And as expected, we're getting pretty close to 12, 11.42 down here at the bottom. So what we're doing is we are clipping the amplitude of our resultant waveform. We're limiting that amplitude by giving the current an easy path to follow and not allowing ourselves to develop a bigger voltage drop over that initial resistor effectively. So that is clippers in a nutshell with bias offset. We don't have to have these sources. We can just use the forward bias voltage of the diodes themselves, in which case we would have a curve that just swings back and forth between V forward, positive and negative, which isn't quite as useful as having it adjustable. Okay, so next we're going to look at adjusting offsets in a sinusoidal waveform. Again, this could be any waveform, I shouldn't say sinusoidal, periodic waveform, but we're going to use sine waves pretty much as our demos, again, because they are the output of rotary turbine generation. Naturally forms a sinusoidal waveform. So that's pretty much what we start with all our signals. Okay. The idea of a clamper is addition of a DC offset that basically references either the peak, positive or negative peak. So what we're going to do is build a circuit that's going to grab either the upper end of the positive going peak of our waveform or the negative and clamp it to a particular DC offset or to a 0 offset. So rather than varying around 0, we're going to vary around whatever the amplitude of a waveform is plus or minus whatever we want to add. So the idea of that is inherent in the idea of a DC offset, which we kind of saw when we looked at ripple being imposed as a time varying signal, kind of being imposed over the true DC we were trying to generate. So a way that we can draw that is a sinusoidal AC voltage source, and then we have a DC source in series. So by the time we get to V out at R and D, what we have is whatever this varying source is plus E. So at these nodes and at V out, we're going to get V in plus E, basically. So it's an addition. So on the positive half cycle, we're going to be adjusting a bit because of the diode. It's only going to let some things go through easier. So, but the basic idea is we've now done an addition of two signals. And this gets important later in electronic communications. We've got a time varying signal plus a time invariant signal. So we're going to see the sum of these out here minus whatever the diode is doing for us. So we can think, well, what's the diode going to do? Well, let's walk around the waveform again. We're going to start out with our positive half cycle, and our V out is going to again reflect the sum of the two. So it's a signal adder. And at that point, we're flowing positive current clockwise towards V out, and the diode is reverse biased, so it's an open. It doesn't even exist. We could just scribble it up. So then we start going through the negative half cycle. Well, the battery doesn't change sign. So now the voltage out at these nodes, which are all at the same potential, notice there's a wire connecting them, is now going to be E minus whatever V in is. Okay, so E is positive, so we're going to have a signal, basically a negative going signal, and you can kind of think about it as running back through ground, because ground is typically connected, as we find out with our grounding loops. So we're going to have a signal on this side that's going to exceed whatever E is giving at this point by the forward bias voltage of the diode. So we're really going to have to apply quite the negative signal of V in before we can open the diode and allow current to flow the other way. So we can say that mathematically by saying the output is going to have to be, it's going to be V in plus E until that sum is less than the forward bias voltage, and it's going to be negative because it's going to have to be having current flow upward from ground. So we're going to have to lower this point below V forward. And since we're already raising it by E, we're going to have to really lower it here. And in that case, we're going to have current that bypasses the resistor and can flow like that. So that's great if we want to displace our sinusoidal voltage by a particular amount. Basically just move it up or down. And in fact, we have the ability to do that in our TINA circuits. We'll go back to our clipper example and just show you where that is. When you've used your time varying voltage generator in TINA, you can pick whichever waveform you want by going into your signal, but you've also got this ability here, DC level. So you can just add that to your signal however you want. And so that will just basically index your waveform up and down up the y-axis by whatever you put in. And so the circuit that we just looked at is doing exactly that. And in fact, we might want to do that right quick. Let's make things easy. Let's get rid of this, just to make sure everybody's got this kind of in their heads. Let's make a simple circuit. Kind of pretend we're using our oscilloscope. So let's see if we can do a quick transient. Look at ourselves here. So here's our waveform with no DC offset. And so let's give ourselves 2 volts of DC offset, because that's kind of what that circuit that we saw was doing minus the action of the diode. So it's just getting you used to thinking of what an offset looks like. Close. So looks the same. We started like this, but our axes values have changed. So instead of going from 12 to negative 12, now we're going from 14 to negative 10. So we've moved the entire works up, this case by 4, so it's doubling that. It's doing 2 on the amplitude. So that's the action of a DC offset. So we've just moved the entire waveform up by a certain amount. Okay, so we'll close this so I don't save it with it all chopped off. No, don't save. I want to keep my clipper. Okay, so let's look at what would happen if we wanted this offset to have some relationship to our signal over here, because what we're trying to do is we're trying to apply an offset that varies with whatever our peak is in the negative or positive direction. So there's got to be some way to put something in here that senses whatever that is and can move with whatever our waveform is. Right now we're getting the same offset no matter what. We want to have an offset that basically is equal to the peak, whatever the peak is. Okay, one way we can do that is to use a capacitor. Because this capacitor is only going to develop a voltage that's equal to the charge it has on it. There's our definition of capacitors, right? The voltage over a capacitor is equal to the charge accumulated on the plates divided by its capacitance. So we're going to put a capacitor in this circuit, and we're going to keep our diode there. We're going to use a really big resistor, which makes this series time constant huge in the forward direction, where we would have to drive current in this direction to ground. So it's really not going to charge up with much positive charge on that left-hand side, excuse me. But then when the voltage signal, our sinusoidal signal, swings negative, it can flow conventional current up through the diode as soon as it goes above forward bias, and now we can pile up positive charge on this side of the capacitor easily, very quickly, because the diode's going to act like a short pretty much once we're above forward bias. So at that point the capacitor is now going to charge up and until it has a voltage that's equal to whatever the input signal is in the negative. And it's going to push back with a voltage that's exactly equal, minus the forward bias voltage of the diode, to whatever the peak was. So by putting the capacitor and the diode together, we create a customizable DC offset that is clamped, hence the term clamper, to the peak voltage of our input signal. So that's the basic essence of a clamper. So if you want to go through that on your own, I've kind of put the stages again in terms of what happens with each waveform, but I basically just talk through that. Forward cycle, not much currents flowing, have a huge resistor, big time constant, no charge accumulation, and the output voltage is basically just going to track the input. When we try to swing back negative, we can flow current. And so we're literally going to be building an opposing voltage to our first negative cycle. So the output's literally going to see the sum of the input, which is going to be negative, and what's a growing positive, V sub C, which is going to kind of cancel out. We're not going to see V out is going to be negligible. And then on the next cycle, we'll effectively have, when the next forward cycle, we'll have V in adding to V sub C, which should be now still be at that peak, because it had no other way to discharge. It can't discharge down through the diode, and it doesn't really have time to discharge through the resistor. So this ends up becoming kind of a little battery DC source that we charged up on our first negative half cycle or two. It may take a couple cycles to get it charged, but it'll be by definition equal to the end peak minus the forward bias voltage. And of course we can adjust that. We can make sure this diode doesn't open until we've gotten above or below V forward with its own DC offset. So we can put a little clamper DC source and change our clamping point, so it isn't just the peak. We can move it around the way we did our clippers, but basically the whole concept is we charge the capacitor to the peak of our signal, or the peak of our signal with a known offset that we put, and not just a constant offset. So let's take a look at that in our simulator, see how it works. We've got a simple clamper. This is Mr. Fiore's example 3.4. So we have a 10 microfarad capacitor. We've got a big resistor, 10K, so we could multiply those two and get a tau and compare that to our very high frequency signal, which is why we're using that high frequency signal here. Have a 10 volt peak amplitude, and we just name that. Let's go through and make sure that's what it is. Yep. Always a good idea to check that things are what they are. And now we are using a clamper source of 5.7 volts, and we have a standard rectifying diode. So this point here is now above ground, going to be equal to right around 5 volts. We've got 5.7. We would subtract the forward bias voltage needed to get over the diode. So this is going to be a steady 5 plus whatever our input can give and whatever voltage the capacitor is going to provide. So those are going to be the things that can vary. But we've now put a voltage source there. So we have to remember that when we have voltage sources in parallel, we tend to and connect them in a single node in parallel. We're going to default to the highest one at any given time. So let's see what that looks like with our analysis. We're going to take, again, about a period and a half of time. And I'll display the legend so we can figure out where we are. So here's the green is our input signal, and we do have a bit of a funky scale. You can see we're going from -10 to +10, so our zero point is right around here. So again, on our forward going signal, let's do some comparisons. Let's take a look. When we're just starting and we haven't applied anything yet, you can see our output is already seeing the influence of this source minus about a half a volt forward bias voltage on the diode. So we're starting out what we would have predicted, that our output voltage is all coming from here. The capacitor's not charged yet, and we have 0 volts coming from our source. So we're going to add to this point something coming from the source and being reflected across the capacitor. The capacitor's not going to charge, so it's not going to develop an opposing voltage yet. Doesn't have time because we've put this big resistor, and of course the diode's in backwards. It's in reverse bias from the standpoint of the source. So we sweep up our forward cycle, and our red curve, which is our output, just tracks it basically. So when we get to the top, we have our original 5 and a bit added to our 10 volt peak, and as we come back to our 0 inflection point towards it, we find that we can't get below a point that is now reflecting that source minus the diode forward bias voltage. So we don't go below that, even though our input peak is low. And as soon as we start swinging less negative, we start to climb again until at this point we're now reflecting the full peak voltage over the capacitor. So we have 10 volts at the capacitor plus what we're getting from this branch. So we have those adding together at point A, so we'd predict we would have something like 15 and a bit. Excuse me, we'll have the full peak to peak. So we'll end up with 20 and a bit, which is what we see, 24.95. So about 25. So that is a demo of clampers. This is the one demo that we had. So major points charging on the reverse cycle to the full peak level that we can get on that negative cycle, plus anything we had coming out of here. So the capacitor wouldn't just charge to 10, it would charge to whatever point A is plus the peak, which is why I misspoke at the beginning with 24. And then that stays, has no way to discharge through the diode, doesn't have time to discharge through the resistor, and so we're adding signals all the way through. So what we would say is that we have clamped our input waveform to 5 volts effectively, which is approximately this minus the forward bias voltage. If we took this source out or reduced its value, maybe we'll call that 0, and reran our analysis, we would expect to see this peak being clamped to just the forward bias voltage of the diode. So we can go ahead and run that, see how that works, and now we've seen our Y scale change, and now we have just 700 millivolts in the negative. So we're seeing 0 minus the forward bias voltage of the diode, which is what we would have expected. So that is a demo of a clamper circuit with a bias offset. So something like this going. In fact, it's exact circuit. And you can simulate this. Here's Mr. Fiore's output. He's superimposed his base curve with his output, so you can see how we have literally shifted this waveform up and clamped it. Its negative peak has been clamped to the 5 volt minus the offset, excuse me, minus the forward bias voltage. Getting tongue-tied. So clamping, the thing to remember is the action is going to be taken on the peak, not on the midpoint, the way it necessarily would if we had an inline voltage source. So that is the end of this lecture, and feel free to run those circuits yourself, predict what you think the output is going to be, and then you can run it and get some practice as well as doing the problems. And this concludes our sections in the course on diodes as voltage regulators. So for our next lectures and next study sections, we're going to be going to a 2-interface semiconducting device, the bipolar junction transistor, which can be modeled as a diode plus other things. So we're going to be building on what we've done with diodes and looking at what happens when we have 2 PN junctions in one device, and how we can start using that as an amplifier to modify input signals and start introducing the concept of gain. So stay tuned for that.